So I'm moving on to chapter 2, and of course I'm referring to the ordering and numbering system at the start of the problem book. That's going to be on limits. All right. Now, I want to see this concept, which might seem new, and I want to see it in the right way. Then it doesn't have to be very complicated. It's really just a way to simplify things we've already seen, perhaps. Let's remember problem. Someone who closed that door, that would be great. The acoustics in the hallway, they're pretty bad. If I look at problem 112, for example, one we've done before, and I look at one of the later ones, perhaps 14, it said if x approaches negative infinity, then what happens to my functions over here? 4x over x squared minus 4. Does everyone remember that we looked at these kinds of problems? Does it look familiar? So we identified what kind of function this is. What kind of function is it? It's a rational function because it's a polynomial over a polynomial. And then, because it's a rational function, I have little shortcuts or ways that that function always behaves that I can use to say, well, this function behaves the same as the ratio or the fraction of the leading terms. Let's write that down. Yeah, I'm going to write it down here. As x behaves like this, getting large in size but negative, 4x over x squared minus 4 behaves like 4x over x squared, because each polynomial behaves like its leading term eventually. This simplifies to 4 over x, and that tells me that as the denominator grows, not the numerator, this is going to become, wrong symbol, shrink in size, and therefore the original function will shrink in size as well. So that's how we handled that kind of long-term behavior question. The good news is that this question isn't really going to change. We are just going to write this in a more compact way. That's all. So limits is the language to help us phrase what's happening here. So let's just say if the answer to this question, meaning the answer that I get there, if that is a number, that means that my y value, or my function value, approaches, let's say, a finite value as x behaves however it behaves. Finite value. Then, if that is the case, we say the limit exists and more we say that the limit of, I'm going to write all the words, and then we're going to shorten it in a second. Limit of the function, which is that function over there, 4x over x squared minus 4, is 0 as x does whatever it does. So this, I think, is the most important section. It's not that the question is changing, it's that we are just saying it, trying to say it in a more condensed way. Bring in this word limit to say that the y value behaves in a nice stable way. If I look at a graph here of what's happening, now I don't know what the whole function looks like, and this question isn't trying to answer that either. But as x goes very far to the left, what does the y value, meaning the function, do? It's going to approach in some way, I'm not sure how exactly, I don't care either. It's going to stabilize towards, where's my pen? Towards a 0 y value. That is what all this says. So if the function, if the graph, if the y values are approaching a specific number, 0 is a number, but it could be other numbers as well, sort of a nice stable behavior. It's getting closer and closer to some number. Then we say the limit exists. We say the limit of the function as x approaches negative infinity or whatever, in this case, is 0. That's still a lot of words, still too many perhaps. The short way to write that is LIM for limit. Underneath that, I'm going to say what x does in this case. And of course, x is going to do different things in different examples. Then I'm going to write my function. And then I'm going to say what that equals. So the limit is representing the issue of looking at the behavior of the function. So the words behind this portion, of course I need to know what the function is. These words, limit as x approaches negative infinity, is really trying to say these words. As x approaches negative infinity, the function behaves like what? Or towards what? And the answer is towards, towards 0. So instead of saying as x gets bigger, negative, then the y value behaves like, all those words are captured in the limit concept. So it's really just a matter of convenience. We don't want to write all the words every time because we want to do a bunch of questions perhaps. The limit is the word that they've decided on to capture the behavior question. And if I see it that way, things are much less intimidating. Any questions on what the limit means, what it's trying to ask? And of course, we need more examples, but if we focus on, it's not asking what is the y value. I can't plug in negative infinity. It's not a number. It's a direction. It's a behavior in the x values. What is the corresponding behavior in the y values? Now, with this new, quote-unquote new, it's not really new, it's just a new way of referring to behavior, we are in chapter 2. But it's not really a new question. Just new words for a familiar question. So I'm going to page to the problems in chapter 2, looking at 2.1, where it's now a bunch of limits that we have to evaluate. 2.1. I'll do a bunch of them. Let's start with something easy. Let's go with number 4. Limit as x approaches infinity of 2x to the 4 minus 3. You put brackets around it, but my function is pretty obvious. There's nothing else there. So, x can do different things. In this case, x is getting really big positive. The limit is, so I need to know my function. The limit is asking, how does this function behave as x does what we say it does? Well, my question doesn't change. The words, the presentation of the question might be different. The question is still the same as the previous long-term behavior question. So I identify the kind of function, it's a polynomial function, and then I know, well, if x goes to infinity, that's the long-term behavior question. So the polynomial long-term behaves like its leading term, and because the word behavior is what's hiding behind this limit, I can say, like I did previously, the function behaves the same as the leading term. But if I'm talking about behavior, I need to put those behavior words in front. And the limit, that LIM with the x behavior underneath, needs to be before the function because it represents the words, the function behaves like something as x approaches something. So I can't say this because the left-hand side is referring to the behavior of the function. The right-hand side is the function itself. How it behaves and what it is won't necessarily be the same. If I'm talking about behavior, I always have to put the behavior words in front to make it clear. I don't care about what the y values are, and those two functions aren't the same. But they behave the same when x gets really big. And then this is a simpler function, technically. And because I have 4 x's multiplied together and a positive 2, let me just rephrase this. This does not equal a number in this case, right? Because we said as x gets really big, then 2x to the 4 minus 3 is going to get really big as well. So in this case, if I look at the graph, something very different is happening between these two examples. I'm still looking at behavior. The question is the same. I'm still looking at a limit, but the answer that I get in terms of that behavior is not the same. In this case, if I go far to the right, the y value just keeps going up. It's not stabilizing towards a specific number. And our infinity answer at the end there is indicating that the y value just keeps growing. It's not going to get close to any number. Whatever number you pick, it's going to grow past that eventually. So it does not equal a number, even though we represent that with infinity. That infinity is not a number. It's a direction more than anything else. So we say the limit does not exist. The limit only exists if our behavior of the function approaches a number. And in many cases, like just basic polynomials, it's going to go up or down indefinitely, doesn't approach a number, doesn't have it's not stabilizing to a specific level. The limit does not exist. Now, in some cases, we understand limit doesn't exist, very important, but we still sometimes write limit as x approaches infinity. My function is over here. We want to indicate a little bit more, because if I just say, oh, it doesn't exist, sure, that is right, does not exist. But I can say a little bit more. I know a little bit more about how the y value behaves, in that it's going up. It's increasing in a positive way. So we say equals positive infinity, but let me be extremely clear, that in no way means that the limit exists. It's just trying to give as much information as we have. That equal sign is extremely unfortunate because it makes you feel as if there is an answer. No, this is just as much information as we have. That there's a difference between going all the way up and all the way down, so I want to at least represent everything I know about the function when x gets really big. The limit does not exist. It has to equal a number. But I write casually equals infinity to show all the information I know at this time. Is that clear to everyone? So there are two answers that are sort of correct. You can just say, limit doesn't exist, move on. But if you want to just represent all the information you have, you can say a little bit more if you know more. Still does not exist. Has to equal a number for it to exist. Let's go with, let's go with 9. Limit x approaches infinity again. 1 over x squared minus 4. So I have to be comfortable now with what this is asking. That's the most important. I see that. It looks really strange. But it's not. It's just trying to represent a lot of words for convenience. That's all. So first I have to understand. It's asking for me to figure out how does that function behave when x does something. And in this case, x gets really big positive. It almost looks like a 2. It's an x. So I identify the function, rational function, which means I need to look at the leading terms. Whether I write more or not, I'm really looking at these guys. 1 over x squared does what when x gets really big? Does it approach a specific number? What is that number?
0.
It is 0. 0 is a number, limit exists. And this also means that if I were to visualize a little bit what's happening here, we're just rephrasing things we've already done. That would be horizontal asymptote that's happening. So things we've already seen, same question, it's just rephrased with this limit word. Okay, so it doesn't have to be new or handled differently, it's the same question. And because 0 is a number, there's stable behavior. I know exactly which way it approaches that line. I don't really worry about that right now. It's going to be from the top, so I might as well indicate that. But later on we'll see that. We'll figure this out easily. It's whether it approaches a specific value or not. In this case, 0. 0 is a number. And then I can do other things like let's just go for number 7. Why not? I've been delaying it. We should. No, let's before 7. Let's do like a number 2. Limit x again goes to infinity. X to the negative 5. What kind of function is that? I don't know. Is it a polynomial? Is it a polynomial? I need to know. Because if it is, then I handle behavior questions a certain way. And if it's not, then I can't use my knowledge of polynomials. Polynomial, yes or no? You have to have an opinion. 50-50, yes or no? How many of you say, yes, that's a polynomial? Wow. How many of you say, no, that's not a polynomial? Okay. Why is it not a polynomial? You raised your hand, you have to have a reason. Just guess. Everyone guessed no correctly. It has to be a positive power of x, and that's -5. I can rewrite this, though, to 1 over x to the 5. And then I see, oh, it's actually a rational function. Simple one, but still. And then I can exploit my experience with rational functions and say that's going to be 0, so the limit exists. Because the numerator is just a 1, and the bottom polynomial has a high degree. Okay, fine. Now it's good to say. I can do more than just polynomials and rational functions. Now I'm not going to do too much, but we have seen other things that allows us to handle other functions. What is my strategy going to be for something like that? That's obviously not a polynomial, not a rational function. Those are my two main functions so far. This is something else. What's my strategy going to be? Just turn the page, leave it blank, next one? Or what can I try? Try to figure out how this function behaves. What do I see when I look at that function? It starts with a T. We've done a lot of them. We've made sequences of them. And then little graphs. Transformation. Because that's built on a basic function. This guy is going to be my square root function, transformed to, well, I'm not loving what it looks like, right? So let's rewrite this first, because I don't want to be caught out with a negative in front of the x. So I'll take out the negative and then write x, and it's going to be a -1. All right. One trap avoided. Now I will replace x with a negative x. And then I will replace x with an x -1. What is happening to the graph? I'll do really fast because it's not a graphing question, it's a behavior question. But I need to visualize what the end result looks like to answer this behavior question. So I have my square root function, sideways half of a parabola. That then becomes reflected horizontally, like that. That then becomes shifted to the right by 1. So this is my end result. So what happens to that function when x goes far to the left? You read it off the graph. Well, it's not the best graph, I apologize, but you can still use it. How does that function, the original function, with that as its graph, behave when x goes to -infinity? What does the y value do? Read it off the graph. What does the y value do? Does it approach a specific number? It doesn't approach a specific number. There's no asymptotes in the square root function. It just keeps going and going and going. Yes, slowly, but it still keeps growing in the positive direction. So it's going to be positive infinity. Now, the positive or negative infinity isn't that crucial. If you say negative infinity, that's totally fine as well, to be honest. The important thing is it a number or not? That's the important thing. Does it exist or not? If you write negative infinity there, I don't care about that either. It's a question of existing or not. This does not exist. You can even say, I don't know. Is it plus or minus? Not sure. But I know it's not a number. And that is the most important thing. Number or not? And if it is a number, what's that number? That is the most important. So I can use my transformations, which of course you spend hours on perfecting, to see what the behavior is when the function is built on some familiar basic function. All right. Info page. So there are many more of them for you to practice in 2.1. I don't think it's necessary to do more. We have basic transformations. Then we have our familiar polynomials and rational functions, and those are pretty much it right now. We only have so many basic functions that we have in our library right now. So far, we looked at limits that look like limit as x approaches infinity of some function, limit as x approaches negative infinity of some function. Those are the two limits. And these are called infinite limits. Because x, the behavior of x doesn't go to a specific number. X just goes to one of the two extremes, either big positive or big negative. But if I'm looking at behavior, there could also be things happening near specific x values. Oops. There are more limits that I can now, there are more behavior questions that I can now write by way of these limits, for example. If I just think of my basic rational function, I'm going to make it a little more interesting. Let's look, for example, at y equal to 1 over x minus 1. What does that function look like? Can you graph that function? The answer should be yes. Very easily, you should be able to graph that function. It's a single transformation. Single transformation. In this case, I just wanted to get away from the y value, from the y-axis a little bit, so I can see what's happening here. In this case, I have a perfectly fine function. It's a nice smooth graph. It comes in two pieces because I have a little problem at 1. A little problem. So there's a behavior problem when x gets closer and closer to 1. And I can use my language of limits to represent that information. And I can say that, well, and we've seen this before, that as x gets closer to 1, the y value just blows up in size, up or down, but it's still not good. It's not approaching a specific number. So we can say the limit as x approaches 1 of this function does not exist. Now we'll come back to this, but the point is that I can also look at x approaching a finite value. It doesn't have to be plus or minus infinity. There could be other behavioral problems in the function at specific x values that I want to highlight and describe the behavior. So it's not about the answer being infinity or not. It's about what happens to the x value. So we'll call these finite limits. It's not the answer, it's the x behavior. Okay. So our the language of limits is sort of a little bit more versatile in that if I'm looking for long-term behavior or issues like vertical asymptotes, I can now represent that with the same kind of sentence, all capturing the behavior by way of this limit. Okay. So we'll come back to this. I don't want to scratch the surface too much here, but first I want to note something, that if I didn't look at x being close to 1, if I was over here somewhere, let's say 3, and I ask you, how does the function and the y value behave as I get closer and closer to 3? Well, if I plug in numbers closer and closer to 3, I am really getting these points, and I'm traveling along the graph towards the point corresponding to x equal to 3. Which will be, what's the y value when x is equal to 3? It's 1 over 3 minus 1, so 1/2. So let's say it like this. Away from problem x values that I can't plug in, or something extreme, or something strange is happening. Away from those. In other words, not entirely true, but if I have a single function, like this is a single rational function, defined at the x value in question, x value, let's call it x equal to c, like 3, or something else. There's no problem there. There's no issue. I can plug it in, I get a y value, everything around it is good. As I'm approaching the value of 3 from both sides, I'm really sort of traveling along the graph, getting closer and closer to the y value that's at x equal to 3. There's no problem at all. So it's a single function. It's defined at, I'll say here, and around the x value of c. I can travel along the graph towards the point. Everything's good. There's no problem. Then the limit, sorry, I'm trying to write my L's a little better. Limit as x approaches the c of the function is simply the y value when I plug in that x value. Meaning I'll plug in the x value and get the y value from the function. So for many x values and for many points, there are no issues. And asking about how the function behaves is equivalent to asking for the y value. The behavior question is more useful when there are weird things and problems and things that I can't just find a y value for. So all this is really saying is, yes, I can ask about the behavior of the function at places where there are no issues, and then it just becomes the y value. There's no problem. I can still ask about behavior, it's just not necessary. And it's the same as just asking for the y value at x equal to c. So the first thing I'm going to try when I see my function just being a familiar function or a simple function but not super familiar, I can just say, well, let's just plug in the x value and see what happens. So that will be my first first thing to try. Let's say here, let's call this let's make a new page actually, so I can update this strategy list that we will make as we go. And sometimes weird things are happening, but in the very simplest case, they might just be tricking you and giving you some simple function with no issue at the x value that they're looking for. So first of all, I want to identify the function. Let's have a look at the function. Is it a single function? Later on, we're going to see functions that come in pieces. What kind of function is it? 2. So I have a limit. I have a limit question, right? That's my function here. Is the function strange? Is it just a straightforward function? First question. Just have a look. If there's any kind of function, as we're building up the experience, we'll see what this means. Then I can try to plug in x equal to c. Now, of course, if this c could be infinity as well, and then of course I can't plug it in, right? But in the case where that c represents a number, maybe there are no issues, and the question is trying to trick me. Just plug it in and see what happens. If I get a y value, then great. Do I have space here? Yeah, I have some space. If I look at problem 2.2, number 2, limit x approaches 2, x minus 1 over x squared minus 1. Now, I look at the function. It's a straightforward rational function. Okay, great. Not expecting anything weird, but I also know that those kinds of functions potentially have vertical asymptotes. They have problem x values. But if my x value in question isn't one of those x values, I don't care. It's a 2 in this case. This guy has vertical asymptotes where? We've done this. We should know what we do as we do it, because it keeps coming up. Vertical asymptotes of that function. Does it have a vertical asymptote? What do I look for? Where do I look to find a vertical asymptote question? Do you remember me talking about this? That's step 1. Do you remember us talking about it? It is problem 1.13. And we did this. Vertical asymptotes. Where do I look to find vertical asymptotes? Look in your notes. Do something. Enable yourself. Be proactive. Sitting back waiting for me is not going to pass your test. It's probably going to fail your test. You have to take the initiative and do something. You're one question ahead of me. Where do I look first? Denominator equal to 0. So I have vertical asymptotes, but it's at x equal to 1. Right? That's not what the question is. The question is concerned with 2. It's nowhere near these issues. So it's as simple as plugging in the 2. This function is defined at x equal to 2. It has no issues. Its issues are at 1. Plug in the 2. 2 squared minus 1. What do I get? 1 over 3. And there we go. Everything's fine. So I don't want to go in expecting the worst every time. It depends on the function, and it depends on the x value that they are asking me to examine. And it might not be one of the problem x values for that function. You can't just assume, oh, this limit, I see a rational function, so it's always going to be an x value where there's a problem. No, I have to look. I have to look. As a side note, I don't want to do the side note right now. One thing at a time. So it's a matter of what is the function, what is the x value, and how do those things agree or disagree? Is it a problem or not? But we have to sort of review and solidify previous concepts because we're going to keep looping back and using those things. An example where we use transformation. An example where we use vertical asymptote knowledge. All those things come back. So you have to stay up to date. So it's as simple as just plugging a number. Fine. But if that doesn't work, am I over here? Yeah. If that doesn't work, if the function is undefined at x equal to c, like, let's maybe take that. Let's take that one. Let's make it 2b. And let's change it to x approaching 1. Same function. So now let's make a different question where the x value in question is the problem one. Obviously, so I go through my steps. I see single rational function, totally fine. I've seen these kind of functions before, but I'm not looking at long-term behavior. I'm looking at x approaching 1. That function has a problem at 1. I can't plug it in. I do check, because if I can plug it in, great, I'm done. But I can't plug it in, because there's an asymptote, there's a problem at that x value. I can still ask this behavior question, though, because this function has a x squared there. I don't know exactly what the graph looks like. So what I'm going to do then is try some things. And it depends on what the function is. For a rational function, most of the time, almost all the time, I'll try to simplify the function and see what, yes, this function might not be the simplest version when I'm asking for the behavior question. It's not asking me for calculate the y value when x is equal to 1. I can't do that. It's asking me for what is the behavior of this function. So I am going to simplify, and that could be by way of factoring. I could simplify that way. And depending on the function, simplify will mean different things. So in this case, I have an x minus 1 at the top. I can factor the bottom as the difference of two squares, x plus 1, x minus 1. And then I see, okay, whoa. There's an x minus 1 at the top. There's an x minus 1 at the bottom. If I cancel those, which I can, it's just multiplication, it says that the behavior of the original function is the same as 1 over x plus 1. Again, let me make this extremely clear. The original function is not 1 over x plus 1. Just like the polynomial isn't its leading term, but it behaves the same. And when I'm looking at limits, I'm looking at the behavior, not the function itself. So therefore I can say the behavior of the original equals the behavior of 1 over x plus 1. If you don't have that limit in front of it, it's wrong. They're not the same function. But they behave the same. And that's what we're interested in. Now I look at this simpler function. Does it have a problem at 1? So now I sort of reset. Yep, still a rational function. Try plugging in the x value in question. Do I have an issue when I plug in 1? No, no issue. No issue at all. It exists. So, yes, there's more in the list that we have to do, but I'll just graph it under here. So what happens to this function, Now, I'm not going to graph the whole thing because people then think, ooh, how am I supposed to know what that graph looks like? I don't care. I care about what happens close to 1. It exists. The behavior is stable and a half, even though I cannot find a y value when I plug in x equal to 1. So it's still, so this function here, undefined at x equal to 1. Yet there's still stable behavior. So let me just think. So at a half, let's say a half sits, no, not a half, no, it was 1, right? At x equal to 1, I have an undefined issue. There is no y value there. Doesn't exist. Doesn't exist. Yet, I can travel along towards that, closer and closer to 1, closer and closer, and it will tell me, yeah, no, I'm approaching 1/2. I can't actually be at 1. But as I'm walking towards 1, there's a graph, everything's good, it's defined. I'm getting as close as I want to 1. I just can't get there. I can't stand on 1. But as I'm walking towards 1 on the graph says, yeah, I'm going to y equals 1/2. Everything's good. As long as you don't stand on x equal to 1. Because I'm only asking for the behavior of the function. Now I don't really care what the graph looks like, nor do you have to know that that is a little hole or anything fancy. The point is that the limit is asking for behavior which can still be stable and predictable, even though there is no y value that I can calculate. All right. So there are a few more cases to update in our strategy, not a lot, but that is the essence. So just focus on 2.1 for now. We haven't finished the next one. And focus on what limits are trying to say. It's asking for the behavior. And depending on the function, that is approached in different ways.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.